Then hi, thanks everyone for attending, even though it's close to the break and we're probably all tired. So I'm Julian from TU Darmstadt in Germany, and I'm a first year PhD student there. And today I'm going to talk a bit about some projects and ideas that I have regarding programming support for local first software. So I was also kind of expecting that we would have a speaker view, so I hope I remember what happens on the next slide, but we're all in this together, right? Okay, so to start with, the subtitle of the application that I submitted was enabling the design of privacy-preserving distributed software without relying on the cloud. So first of all, I'll start with what actually is local first software and what is the problem that I see with the cloud. So if you think of modern collaborative and distributed software, so something like Google Docs or any to-do list or notes application, which allows you to collaborate with other people, the architecture pretty much looks like this. So you have different devices, and they connect to the cloud, which is some network of servers which are standing somewhere. And then when you send updates to the cloud, you get some update back of the refreshed state. So what's the problem that I see with this? In this talk, I'm going to focus on 3 key points, although you could probably come up with a much longer list. But the first one, which is probably very obvious, is offline availability. So whenever we use cloud applications, we can't really use them when we're offline. So when you're traveling on the train or on the plane or wherever you're off the grid, you can't really rely on this kind of software. Okay, then the second problem that I see here is data ownership and privacy. In most cases, the cloud really functions like a black box. So users have no idea what's going on there. They don't know where their data is stored. Sometimes they don't even know in which countries these servers are standing in. And they also have no idea how their data is processed. And they also can't really influence that if they want to use the application. And this also directly leads me to the third problem that I see, which is user agency. So if the cloud someday disappears, like in the slide, or in other words, if the service provider someday decides to just stop offering their cloud service, then users lose the application. If you think of plain old applications that run on your local device, nobody can really take them away from you. I mean, they will generally continue to function for a while. They might contain bugs, and if you're unlucky, those bugs will never get fixed, but at least you have the application and you can continue using the version that you have, which is not really the case for cloud software. So an obvious question that you might ask yourself is, can we do better? Can we somehow allow collaboration and all the nice benefits that we have from cloud software, but tackle these problems that I just mentioned? And local first software tries to do exactly that. The term actually comes from a 2019 Onward paper from Martin Klapman and others. And the idea here is basically that we want our software to be similar to Git. So everybody has an own local copy of the data which runs and lies on your own device. So this would look something like this. So we start with several devices which each have their own copy of the data, and you can just continue using your application locally because it's local first and always works even without an internet connection. But we still want to be able to communicate with others, and similar to Git, this would lead to a system model where we can send updates to others more in like a peer-to-peer manner, and we can also merge these updates into our local application state to collaborate with them. And we could even use the cloud again, but this time more like just another peer in this network. So the cloud would not be the single source of truth that we had before, but it would just be another service that we send our data to and that we get updates from. Okay, so how would you build these applications? Normally, or the standard way to do this right now is through so-called conflict-free replicated data types, or CRDTs. And CRDTs are special data types which ensure that when you merge multiple versions of the data type, you never get merge conflicts. So if you ever use Git, you're probably familiar with the problem that people end up with divergent states, then you try to bring them together somehow, and that is complicated. So CRDT solved this problem by defining how you could always merge two versions together without a conflict. So to illustrate this a little, consider something like a distributed calendar application. So I could, for example, on my phone at a lunch meeting, and then on my laptop, I add the group meeting, and then at some point, my laptop sends an update to the smartphone, which merges the changes. So you see that the CRDT here simply has set semantics, basically. So we have two sets, and whenever we merge updates, we just take the union of the set. Cool, right? So now you could think problem solved. We just use CRDTs to build all of our applications, and we're done, right? Well, not really. The problem is that CRDTs only offer a certain level of consistency, which is often called eventual consistency. And for some applications, this is just not enough. So imagine now you wanted to use your calendar not only to store your personal meetings, but now you also wanted to store your official vacation days. And your employer might enforce a certain condition. So they might, for example, say, well, you have 30 days of vacation in a year, and you're not allowed to enter more than that into the calendar. So what happens if we do this with CRDTs? Then something like this could happen. So I add a vacation of 22 days on my smartphone, means I have 8 days left. But notice that this update does not arrive on my laptop. Maybe my phone was offline at the time I did this. Then sometime later, I add a vacation of 10 days on my laptop, which thinks this is fine because it does not know if we have an update. And once I merge the two states, now I suddenly have used more vacation days than I was actually allowed. So this is a very simple example of what I call a conflict. So in this case, we have two conflicting operations which should not have been allowed to be executed concurrently on two devices, which is what happened in this device, in this setting, and which is what would happen if you just naively apply the CRDT approach to software with specific safety guarantees or specific correctness properties like the one that I just mentioned. So how can we fix this? So the idea of this work is that it's pretty much, could we develop a programming model, or could we come up with a programming model where we can systematically reason about these kinds of conflicts? So can we somehow inspect a given program and automatically tell the programmer which kind of conflicts could arrive in this setting? And to this end, I'm currently working on Law, which is a language for local first reactive programming. Now you already know the local first part, and I'm getting to the reactive part in a bit. So the design goals of Law were twofold. The first one is that we wanted a simple and unified programming model for local first programming, which doesn't really exist so far. So far, we only have these CRDT libraries that you can use in your application, but that can lead to unexpected side effects, as we have learned before. The second goal was to see, okay, could we actually use automatic deductive verification to check which kinds of conflicts could happen in the program? So how do we do that? Basically, Law builds on three programming abstractions. The first one are interactions. So if we stick to the calendar example, we would have two interactions. We have an add vacation interaction and an add work interaction for adding work meetings and vacation meetings respectively. So interactions basically model how users or the outside world can interact with these devices in the distributed peer-to-peer network that we've seen before. The second important part that we need for the verification bit are invariants. So this is something like no employee may take more than 30 days of vacation, which expresses the safety properties or the correctness properties of the application. And then finally, and this is where we get to the reactive part, we have reactives. And reactives allow you to declaratively structure the data flow of your program. So this essentially defines the structure of all of these devices that communicate with each other. So in this example, we could, for example, say, hey, we have one vacation reactive and one work reactive. And those two are source reactives, which means that each of them encapsulates a CRDT. So we have one CRDT for vacations and one CRDT for work. And now the cool part about reactive programming is that it allows you to define derived values. So we could, for example, say, hey, we also want to define an all appointments derived value, which always simply displays the union of vacation and work. And since we're doing reactive programming, the reactive runtime would assure you, or would ensure, that these derived values always get updated automatically. So whenever one of the inputs changes, so like the top nodes in the data flow graph, the other ones get updated automatically. And this also greatly helps our verification goals, because these reactors kind of tie together the first two components. So they tell us how interactions and invariants relate. So if you think about this invariant here, then we can specify this invariant without really needing to reason about the whole structure of the application. All we need to know is that we care about the remaining vacation. So I can basically specify this invariant without knowing how this graph looks like. All I know is that I care about this remaining vacation node down there. Now, because we have this data flow graph, and I should probably also mention that these graphs are static in law, so they are statically defined in the input program, we know that there's exactly one source reactive which can actually affect remaining vacation, and that is the vacation reactive. So in turn, we know that we only have to consider the interactions which modify the vacation reactive, so in this case, at vacation. So whenever we want to verify that this invariant holds for the application, we only have to consider the interactions which affect the affected part of the data flow graph. Okay, but how would we verify this in practice then? So this is an overview of our current implementation, and the idea is the following. The user basically gives us an input program which consists of the three components that I just explained. So we have reactives, invariants, and interactions. Then afterwards, we perform a graph analysis, and this basically systematically does what I just explained to you. So we basically check, okay, which invariants affect which part of the data flow graph, and which interactions change which part of the data flow graph, and therefore which interactions are relevant to which invariants. Then for each relevant pairing, we translate the input code from our law language into an intermediate verification language. What we use here is the Viper verification toolchain. So the idea behind Viper is basically that it has an intermediate verification language that you can translate your language to. And then Viper has several SMT-based backends which automatically try to verify the stuff that you put into. Okay, and then basically what Viper gives us is it can tell us which kinds of conflicts can happen in the application. So it first tells us which interactions could invalidate an invariant when run locally, but it also tells us if it finds two conflicting interactions which should not be run concurrently. And in this case, we use this information in the program code generator, where we basically put in our DSL and all the conflict information, and then we can use this to synthesize a program which automatically coordinates all the interactions that are conflicting. So basically, whenever I call an interaction that does not conflict, I can just do that locally. But if there are some other interactions that conflict with it, then I would have to coordinate with the other devices in the network in order to prevent a conflict. Yep. And we currently compile these applications to actually executable Scala implementations. Okay, so this brings me to the evaluation part of my work. And here we basically try to answer two research questions. The first one was, does law actually facilitate the development of safe local first software? Is it expressive enough to implement real applications? And the second one was, is the verification procedure that we're proposing actually efficient enough to be used in practice for real-world applications? In order to evaluate the first one, so far we have implemented several smaller case studies, but also the TPCC database benchmark, which might seem unusual for a local first application, but the good thing here was that it gave us a larger application or larger specification of a distributed system, which has several consistency criteria which must hold at all times. So we already had some invariants that we could directly translate to law and which we didn't come up ourselves. For the second part, we basically evaluated how long it takes to verify different combinations of invariants and interactions in the case studies that we've implemented. And for the smaller case studies, every combination could be verified in around 5 seconds or even less. And for the TPCC benchmark, the more complicated ones took around 15 seconds. So we still think this is like a reasonable time that, and you could probably even think about including this verification step into a compiler actually. So you could verify in the compilation process that your program actually holds the guarantees that you want to do. Okay, but since this is the Doctoral Symposium, I want to end with an outlook and some future ideas that I have on continuing this work. And I'm also very happy to get some feedback on these or to start a discussion with it. So the first one that I'm really interested right now is actually empirically evaluating that. So I said that one of the goals of this work was to simplify the development of local source software, but so far we have only really evaluated that like anecdotally. So we have our own implementations of applications, and we think it works quite well and it is simpler. But what I would really like to do is to actually perform a user study and let some people use law and maybe even compare it to other approaches that they would typically use to program local first software and get some feedback on how they like it and what the current problems with this approach are. Specifically, one approach of these, one problem that you commonly see in these automatic verification approaches is that users need to write specification, right? So in our approach, they have to write these invariants which they want verified. And here I would find it very interesting to evaluate how hard programmers actually find it to express these invariants. So is a programming model that uses invariants as like first-class citizens, like we do, is that really practical, and is that really something they would like to use? Then when it comes to extensions, there are also a lot of things on my mind which could help designing local first software, because so far law only tackles some of the problems, which are safety properties, for example. But one exciting question that I see here is, could we also include access or security properties in the invariants and then give programmers some insights into the code that they programmed? And the second one is different conflict resolution strategies. So as I explained, whenever we find two conflicting interactions right now, we force them to be coordinated. So that basically means that two devices can never run these interactions concurrently. But you could also take a different approach. You could, for example, expose these conflicts to the users like Git does. So you could display them a merge conflict, and then they would somehow have to handle this themselves. Another way you could do this is using like a token-based approach, where you could say something like, okay, every device on the network gets 10 tokens or 10 tickets, is probably a better way to call it, for conflicting interactions, so they can perform these 10 times before they actually have to check in with the others again to request more tickets. And I think it would be very interesting to look into how you could systematically evaluate which conflict resolution strategies are viable for which invariants that programmers specified. But this is future work. And with this, I basically thank you for your attention, and I'm happy to take questions.
Okay, let me start with the same question as we asked you before. So you mentioned your thesis of the future work. Like, you know, which one is kind of like the first step next? When do you think you'll have enough to say, I'm going to graduate now? What will that look like?
Yeah. Yeah, so as I said, I'm still quite at the beginning. So we actually have this law system kind of done in the current version, and we have a paper in submission about that. But what I really would like to do next is tackle this empirical evaluation part, because I could feel that could really provide very valuable insights also on what of the other directions are more promising and what actually addresses the problems that users have and that programmers have in this local first space. So this is the one that I'm looking into right now. But I do not have much experience in that, so I currently do a lot of reading actually to see how other programming languages were evaluated empirically and how you would design user studies and this kind of stuff.
Yeah, user studies are certainly a thing that people find hard. It's useful to have someone around who has done this before, right?
Yeah.
There's likely also some sort of process you have to go through to get permission to work with humans.
Yeah.
Probably knows more about this.
Oh, well, possibly, yeah. Actually, I had a different question I was going to ask.
Yeah, sure.
The story you told was a compelling story, and I like the vision. I'm reluctant to trust my data to the cloud too, because I like to work offline and I care about my privacy and so on. So this is all really good things. I want to probe your story though a little bit in
Sure.
the way it flows, right? So you talk about these issues you'd like to solve, and then you go in the direction of CRDTs, which is kind of an interesting twist. I mean, they're a hot topic right now. And then you say, well, there's weaknesses of CRDTs, so let's look at verifying properties we want.
Yeah.
What's interesting is that to verify them, you actually have to synchronize, right? And so you actually move into a different area of the problem space. You're going to sacrifice. CRDTs are all about availability, and for at least the sample problem you described, but probably a lot of these problems, you're going to have to sacrifice that availability to get the verification.
Exactly.
So, I mean, I think where I think you kind of came around to it at the end where you were talking about future work and the fact that, okay, maybe there's these alternative solutions that allow some availability, like kind of pre-allocating resources to the edges. But I think there's a little bit of lack of clarity, maybe at least to me as a listener, thinking you're going in one direction and then seeing you come back to another direction.
Yeah.
And so I don't know if I would do I don't know if the detour into CRDTs is effective in that sense, right? Because it kind of distracts me from your goal that you're gonna focus on in the end.
Okay, thank you. Yeah, thank you. That's a very insightful comment. One thing I would like to respond to that is, yes, we do somehow give up on what CRDTs offer us, but we get other guarantees in exchange, right? So basically, when our verification tells us that we have no conflicts, then we basically have a CRDT-like system where we don't have to coordinate everything. But whenever the system finds a conflict, we somehow do have to synchronize. That's totally right. But I do believe that systems like these could actually help developers make more educated decisions about what kind of system they actually want to have. So, for example, when they find out, okay, I wrote a lot of invariants, a lot of nice properties that I would like to have, but this leads to basically synchronizing everything, maybe I have to drop some of these guarantees. Or maybe I have a system that I simply can't implement with this CRDT approach. So I think there's some value in learning how your safety properties that you're aiming for, how they affect the system that you need to build in the end. That said, I do also think that only using synchronization as a conflict resolution strategy is not enough and probably not very appealing for a lot of people programming local first software. So it would be good to offer some alternatives like the ones that I mentioned.
Okay, good. Well, I mean, I think your explanation helps me understand that. One thing one thing just exploring that you could use as a way of kind of squaring the circle would be to talk about explicitly this trade-off between availability and you know, possible properties that you might need, and position your work as partly helping people find the right trade-off between those for their particular problem.
Okay. Yeah.
Anyway, I think I like the place you're going.
Yeah.
I'm just like brainstorming a little bit about kind of how to get there in a way that kind of brings people along the path in some way.
Yeah, that's very cool. Yes.
So I'd like to pick up this business about testing the programming system with users. And I think the model that I'd like to refer to is Green and Blackwell and Petrie's cognitive dimensions model.
Okay.
And particularly the programming activities that they explicate there. Because they make the point, right, that when we work with programming languages, we're not always creating code, we're often modifying code, we're often reading code, there's lots of different things in there. So, in particular, in your system, what do you think is going to be the distinctive activity which will really show whether this is beneficial and it will work with programmers?
Okay, yeah, that's a very good question. As I said, I think one really crucial part is, or are these invariants. So it's basically coming up with specifications which correctly capture the behavior that you're actually aiming for. So I think this is one part that could be challenging. And the other one that is probably quite unique about the system is this combination of distributed programming and reactive programming. So you kind of, it probably definitely helps if you know some about reactive programming and if you're used to languages like Elm or to Facebook's React. So this way of thinking in data flow graphs, because this is really crucial to the idea. Yeah, so it's probably these two parts. First, like defining the data flow, designing the data flow of your application, and the other one is specifying the behavioral specification, like the invariants that you're aiming for.
That sounds reasonable. I think for the second one, the reactive programming, if we think about the work that's done in, what we used to call end-user programming, and which nowadays we seem to call low-code, no-code kind of things, there's lots of examples from this, going back to spreadsheets and the kind of work, for instance, that Margaret Burnett has done with the different spreadsheet growth. For the first ones, the coming up with invariants, I'm guessing that would be a challenge. Because in the in the course of ordinary programming, that's not the way we think about programming, or rather, it's not the way lots of programmers think about programming. So I wonder if there might be some way to sort of have a conversation to kind of tune that and see the effects of that, rather than putting the program away and trying to sort of calculate an invariant and putting it in. Might that be a sort of option? Basically, a kind of see examples and try out things until it's doing what you want.
Yeah, that's a very good point. I think in some way this goes into the direction of what I already hinted at with, okay, like adding invariants and taking invariants away kind of gives you a feeling of how the system responds to different requirements that you throw at it. But it's definitely a good idea, and I think worth looking into how we could integrate this more into the current programming model. So this interactive aspect of trying out different configurations, maybe.
So what would be a classic kind of exemplar kind of programming? So say you're
you're writing the textbook or the blog post on this to make people think, wow, this would be so cool. What's an actual practical example that you would show to? I mean, for instance, it reminds me a little bit of the Meteor substrate that was created a few years ago, which was essentially reactive programming as well, right? And they had a, they had a kind of a score sheet kind of thing where the score sheet got data from different sources and stuff like that. So what would be your kind of, killer example?
That's a good question. So actually, reactive programming is relatively prevalent already in this domain. So as I said, there are a lot of especially web programming libraries which build on reactive programming. So if you think of end user web applications, something like a calendar or some Kanban board, something where different users can interact. So these are typically the applications that you would program in these systems. And I think this is where our solution could be really useful, because now we can have essentially mixed consistency applications, which offer more guarantees than you would usually have, and which offer some operations which require synchronization. But I'm afraid I do not have this one killer app right now, which is good to sell these.
I'm tempted to think of some sort of network game.
Yeah.
Where the state ends up being coordinated by different actions.
Yeah. Yeah, that's a good point.
So, along with the example that was already shared, I think one more example could be high frequency trading or high frequency message exchanges. So over there are possibly ways of getting conflicts, especially with balance getting updated, which bit actually works better than the other. I think that could be another application for compliance.
Any final questions or comments? Great, then let's thank you again.